So we're going to talk about Mary doubling for small sets in SO3. And in this talk, we only care about real groups. So I will write SO3R just to save some time. Everything is real. And so it's about non-commutative groups. But we only in this talk, we only care about two model cases, just to make sure everyone can follow. So we only care about SO3. Just in mind, like all the group I mentioned are like either SO3 or SO2. So just write one definition. So SO3R fill in 3x3 matrices. Don't have to transport this one. And also determinant this one. Here. And SR2. So this is Q by 2 by 2 matrices, real matrices, with determinant 1. Just these two groups, two model cases. And I just mentioned some basic properties of these two groups. So both of them are locally compact. Because, for example, SO3 can equip with embed in R9. It has 9 entries and use real manifold topology. So both of them are locally compact and connected. That means all the closed-up group has merit 0. So that means when you study doubling properties, you don't need to worry about co-separate or like subgroups, because subgroups have smaller dimension. Right. What else? Yeah. So both of them have dimension 3. They are 3-dimensional group. And maybe I should mention, okay, just write down connected, 3-dimensional. And both of them contains circle group and a closed-up group. Contains circle group and subgroup. Here circle group, I mean SO2 like circle. Dimension 1. And both of them don't have dimension 2 closed-up group. So all the reasonable subgroup has dimension 1. Okay. There's some difference. So SO3 is compact and SO2 is non-compact as topological space. And so maybe one more thing is, since we are studying doubling constant, we have to have a reasonable notion of size. So the size we use here is higher measure. And higher measure here, so both of the groups are good. They are unimodular because they are locally compact. So by a famous result of higher, we have unique invariant higher measure or left invariant higher measure. But here, since they are unimodular, they also right invariant, means the measure here is a nice generalization of cardinality or Lebesgue measures. So they're nice. Means there is this unique mu. So mu x is mu xg. They're invariant. So SO3 is compact, and all the compact groups are unimodular. SO2 is not compact, and not all the non-compact groups are unimodular. It's quite kind of special. So the question I want to study, the question here, is a question by Manuel Brilliard and Ben Green. They ask if A is a subset, let's say open subset, of my SO3R group, and A has sufficiently small measure. Sufficiently small. And do we have the following inequality? Here, as usual, A squared just a product that A times A, meaning all the collection of pairs A to B, where both A and B are in there. So maybe one thing I want to mention, so here, the measure is unique, autoscalars. And when the group is compact, since the whole space is finite, we just normalize the measure to make the whole group has measure 1, to make sure there's no like confusion on this smallest assumption. Okay. Okay, maybe I should just write down the results first, and then talking more about motivations and how we prove the result. I want to mention the theorem by myself and Min and Risham. So we essentially show this is true. Yes, it is true. So maybe I write it in this way. For every epsilon, there exists delta such that if A is an open subset of SO3R with a measure smaller than delta, we have this UA square is bigger than 4 minus epsilon. So this is a statement. And here's the openness assumption. It's not really essential. We just want to make sure A square is measurable. You can replace it by compactness or even measurable set. We also obtain an asymmetric version for both A and B. Maybe I should mention here. We have a Bromikowski type inequality. If you further assume this red color, mu B is also smaller than delta. Then what you can see is 2 minus epsilon. Have this sort of inequality. This is not exactly correct. We have one more assumption. So A and B should have similar size. And this is the thing I really want to remove, but I cannot at the moment. Let's say mu A is smaller n times mu B. It's bigger than mu B by n. Have something like n. So the reason I would really want to remove this assumption because in the actual applications, like as a parametric type inequality, I really want to make one of the size super small. But now because of this constraint, I cannot do that. So I think that naturally this is an open problem, like what if you remove this assumption? Okay. But these are the statements of the main result. So maybe I should ask any question about statement.
Maybe it should be obvious. Why is 4 or 3.99 a natural?
That's a good question. Actually, it's not quite obvious. So I will explain, I will talk about it in a second, but that's a good question. So I'll explain why we have 4. Because if you know something about Bromikowski inequality, you know the growth, the doubling constant is sort of like 2 to the dimension and the group of dimension 3. So probably it's like 8 or something, but it is 4. I will give you some constructions. But I guess before that, I want to mention some motivations to motivate the problem. So why we should care about these problems, this type of.
Before you do that, probably obvious. Is the order of quantifiers for all epsilon and for all n there exists a delta?
Yes, delta depends on epsilon and for asymmetric version.
Again, as big as you like, as long as you make
Yes. But the thing is, you cannot let A goes to 0, one of side goes to 0 because of this dependence. I mentioned some motivation. So one of the first motivation is we want to study this type of problem quantitatively, the study of approximate groups. I think in Jacob talk and Hui's talk, they mentioned something about approximate groups, but they didn't really define it. So I give a quick definition of approximate groups. I'm not really going to use the definition in the talk, but it's good to know this, and I will use the notion of approximate group. So if you have A such as G, is a K approximate group. If firstly A is symmetric, means if little a is an element in capital A, then A inverse is also an element there. And A contains identity, I'll just say ID within A. And A squared can be covered by K left coset of A or K left translate of A. A squared can be covered by X times A with X upbounded by K. It's a finite set. Here. So approximate group is important and has many applications. It's easier to study than set with small doublings because you have this covariant type property instead of just measures. It's different from set with small doublings, unlike in abelian group. So in abelian group, they are more or less equivalent. Being approximate group and having small doublings are equivalent. But in non-abelian settings, they're different because, for example, we can choose A to be a proper subgroup H union a point X, which is generic. For example, it's not in the normalizer of H. then A times A, you can verify A times A is small, but A times A times A is big. And in particular, it is not a proximate group. But a famous result of Terry Tao shows that if you have a approximate group, you can find a large subset of it behaves like a small doubling set. So actually, they are more or less morally equivalent if you don't really care about quantitative bounds that much. So I'm not going to talk about a difference between doubling set and approximate groups, at least in the first part of the talk. But I want to mention the fundamental result in this area. It's a great result by Breda, Green, and Tao. They obtain a characterization of finite approximate groups. So let's say if A is a finite approximate group, then you can find another set B, which is not to B. B is inside A to the fourth. If you believe A is like approximate group, then A to the fourth is already have the same set as A. So B is small. B is K to the 1. I believe the bound should be K6 approximate group. Such that firstly, B is not too small because, for example, we want to show B is not identity. Otherwise, it's trivial. A can be covered by finite translates of B. By L, a constant only depends on K. Process of B. Secondly, the group generated by B is almost abelian. So that's a key thing. Because sufficiently non-abelian groups, it's really hard to have A times B equal to B times A, say, make the set as small doubling. So here the correct notion of being abelian is a nilpotent group. The group generated by B has a nilpotent, I'll say D-step nilpotent. Group of finite index. G is bounded by 6 log K. It is not only like a generalization of Feynman type result in all groups, but also a quantitative version of Gromov theorem on group of polynomial growth if you're familiar with that result. So it has many applications.
So what's G here? G?
It can be any group. Yeah, once A is finite. Yeah. You can just consider the group generated by A, I think. Yeah. Okay. So some comments about these results. So firstly, maybe you notice this L and this finite index. I didn't mention any bound. And they are not, the proof is not effective, so there's no bound. And I think it's one of the major open problem in the field, trying to determine the bound. It would be very interesting to get any quantitative bound. Okay. I mean the structure. So here, the group generator B is not nilpotent, but virtually nilpotent. I mean that. I mean, there are like more precise structure about new progression type structure, but I won't talk about that. I'll just focus on group.
I think if you want to get a bound on that, index, if you want to get a bound on that, then you have to quotient something. If you,
Yeah.
if you want to be finite but not unbounded, then so
Yeah. This is just one of the simple form of the result. And so this is about finite approximate groups. What about other settings? So I want to say firstly, I already mentioned those are not quantitative. And we want to really understand those type of results quantitatively to get nice applications. And also you can ask what happens if you have infinite approximate groups. I mean, there are two directions orthogonal to each other. One is what if you have an open set, a positive measure set. So I want to mention open pre-compact approximate group. Approximate group in a locally compact group. The characterization result is obtained by Cardinal. But it is unpublished, unfortunately. So this is So I've been told by Arturo, a student of Ushasky. He told me actually Udi also independently proved this result in one of his course. So after the BDT paper appeared, so I think Udi gave a semester-long course on the result, and there he not only recovered BDT, he also proved locally compact group version due to Arturo. Okay, he told me this. And another direction is discrete approximate groups, which is called approximate lattices. And this is only the result is only obtained recently by Udi Plasky and independently Simon Machado. Okay, so these are the history of approximate groups. And the reason at the very beginning I care about this continuous setting, one of the reasons is if you want to understand the proof actually use Lie model theory, the 2C model theory, pass to limit and then transfer everything into continuous setting. So you have to understand the first step, the continuous setting quantitatively. And also the cardinal result also is not quantitative at all. It's also ineffective using Lie model theorem 2 or 3 times. I think same as approximate lattices. There you have to use quasi-Lie model theorem obtained by OD. Okay, so this is the first motivation. We want to understand things quantitatively, so we want to understand the continuous setting, the first step. And secondly, like also part of motivation is from geometry. So we want to understand Minkowski type inequality and isoperimetric type inequality. So I didn't mention Minkowski there, so because I want to mention it here. Here's the classic result by Minkowski. And Minkowski. I think in 1880s or 1890s. So they prove a nice result in Euclidean space. So if A and B are two, let's say still open set, make life easier. In D-dimensional Euclidean space, then what we have is the Lebesgue, so here mu is Lebesgue of A plus B to the power 1 by B. It's at least mu A to the power 1 by B plus mu B to the power. So here, if you plug in A equals B, you have A plus A equals at least 2 to the D times the of A. And also the inverse, if you have equality, then AD must be a homogeneous copy of the same convex set. I think if you care more about the inverse type theorem, we can talk to Maris. He's a true expert. Okay, so this is about Minkowski inequality. It's like Minkowski proved it in 1890s for a convex set. And then later it's generalized by a Russian mathematician called, that's what I need my notes. Lusternik. He proved it for all, okay, I just want to check that out. The Lusternik for all variable sets. But his proof contains some error on the inverse part. And eventually corrected by 2 British mathematicians called Macbeth and Henstock and Macbeth in 1956. So the most correct version, let's not compare this. Not the correct version of Minkowski. And in the same paper, they asked whether there's a Minkowski for locally compact groups. And if you care about locally compact groups, you know, the classification result, like Hubert fifth problem, very soon you realize you have to work on Lie groups, real Lie groups. And so probably the most simple case of the compact simple Lie groups is SO3 because it is a simple group. It is a simply simple group because it has lowest dimension, 3. Okay. So their question is study Minkowski for different settings, non-compact groups and compact groups. And the reason we also care about small set is potential application of isoperimetric inequality. So you want to keep a set large and make the other side very small, like a ball or a neighborhood of a cube, whatever, depends on the space. Okay. So these are Minkowski type inequality. You can argue that Minkowski is trivial for compact groups because you can take A equal to B equal to G and you have no expansion there because A times B is just G itself. Yeah, you can do that. But here we care about small set in compact groups. I think for that formulation, if you only care about non-compact group, it is mostly resolved by myself, the same group of authors. Same. Yeah. Myself and Min and Ruixiang a couple of years ago. maybe except the only SL2 tilde, if you remember the problem mentioned in the open problem session. That is one of the only remaining case. I will mention why that's only remaining case because I will use Minkowski as an ingredient in the proof. So this is a second motivation. And the third one we care about, and also your question about constructions, is a connection to harmonic analysis, which is called Condy-Stein phenomenon. So Condy-Stein essentially, I think Condy-Stein phenomenon is proven by Colin, essentially telling us if f and g are L2 function in SL2, what we have is for every p bigger than 2, it's involved. In SL2, non-compact groups. And if you plug in f and g to be indicator function of A, or you decompose the function into level sets, this implies the value of A square is bigger than the constant depending on the epsilon mu A 2 minus epsilon. But this is essentially the Condy-Stein phenomenon. And the epsilon is removed by Inoscu in around 2000, which is called the endpoint estimate of Condy-Stein phenomenon. So one of the reasons we care about the minimum doubling characterized as minimizers is trying to understand what is the endpoint estimate of the Condy-Stein phenomenon. I think except for SL2, the problem is open for other groups to obtain a sharp estimate, endpoint estimate of Condy-Stein. Or in the other case, try to remove this epsilon.
What does an endpoint estimate here look like?
It is a bit complicated. You have to write it as a rearrangement of inequality. We have F colon G inner product with H, and this is I think the inequality just I cannot write it down immediately, but it's like when FG and H are one bounded function, and then the other set of inequality is when they are indicator function of small tubes in the symmetric space. I will mention in the context. You can write it down. But you really want to understand the doubling and not remove the epsilon in the other group of rearrangement. The question. Remove epsilon in groups of rearrangement. Go back to this board. Okay, you may probably ask, Minkowski is about linear growth, right? Like a square is 2 to the d times a, is you only have a linear term. But Condy-Stein has quadratic term. But what are the relation between yes,
Range of P.
P is bigger than 2. So you can apply Cauchy-Schwarz to obtain for a whole set of problems. But here you want to remove epsilon essentially corresponding to P equals 2. But in the V curvature of norms. Okay, cool. So now I want to give you a construction and tell you more about connection with Condy-Stein from the construction and answer your question at the very beginning. So why we have standard 4? So SO3, the nice thing is, it's also known as, probably I forgot to mention, a 3-dimensional rotation group. It's some, yeah.
So in which settings is this inequality known?
I think the classic paper calling it for SL2 are, and I believe later it's proven for all non-compact simple Lie groups. I'm not sure about semi-simple one. I think for all compact simple Lie groups, it is known.
Okay, and then the removing epsilon is only over R?
It's only over SL2R, as far as I know. I think in the same paper, Inoscu asked a question like to remove this epsilon. Well, you can write down the version for asymmetric version. If you, okay, I will write down the construction. From there, I can come up with an inequality with asymmetric A and B. And there is a question asked by Inoscu in his original paper, try to understand this sort of rearrangement type inequality in other groups of real rank 1. So real rank 1 is important. If you have higher rank, you have some logarithm term depending on the rank. I think it's R minus 1 over. If you have something like log mu A to the power rank minus 1 divided by 2, we generate also conjecture. But I won't mention too much about that. It's just about you want to study doubling behavior. And so the construction why we have 4 and why there's any connection to a quadratic equation, because we here everything is linear. I don't know how to. Anyway, I'm taught. I think I could. So yes, the construction is SO3 naturally has an action to the sphere S2. With isometric group isomorphic to the circle group. Let's say SO2 circle. So how to see that? Well, we have a sphere. Let's say we have a S2, and we choose Z as my north pole. And since SO3 is a natural 3-dimensional rotation, it will rotate Z to some other point, right? The element of SO3 will rotate G to some other point, but not quite. Some element fix Z. For example, all the rotation around Z axis will fix Z. So that's why it has a non-trivial isometric group, isomorphic to the circle. Yeah. Okay. Cool. So you have a nice action, and now we define a set looks like a small cap. Theta. So within the range of angle of theta with the north pole. So I define my A theta to be all the element in SO3, so that the angle of D and G act on D is smaller than theta. By a nice integral formula, we know the volume of A theta in SO3 is exactly the area of this cap, little cap. And the area of little cap is known like 2000 years ago. So we know the measure of A theta is something like sine square beta by 2. Okay. We also know that, okay, not that trivial, but you can see that A theta square is inside A2 theta, because you move a point twice, it's still within 2 theta angle of the original. Now that you have A theta square is bounded by A2 theta, just plug in sine square theta, and this is 4 sine square theta by 2 cosine square theta by 2. And in general, you know, this is smaller than 1. So that's why you have something smaller than 4. Only for small enough set. For bigger set, you will have something super close to 2. But now you can have a conjecture. It's very natural conjecture. This is actually the optimal example, even for large set as well. So I call it a strong Brenner-Green conjecture. Okay. All right, conjecture. Usually it's a theorem, but it's not. I just said this is the only case. Okay, cosine square is 1 minus sine square. So the real behavior is if A is an open subset of SO3, and we're just assuming A is smaller than half, because otherwise A square will be the whole group. Then the conjecture just tell you, conjecture, not really tell you anything. Formula A minus formula A squared. So you should have the error term quadratic on the measure of A for the whole range of A. Well, it is a minus sign. You can arguably say, I don't really care about small term. I only care about main behavior. But you can, nothing stop us from working, generalize this construction to SL2. Because SL2 also has real rank 1. So in the symmetric space, the remaining metric in this manifold is unique. Invariant remaining metric is unique. So here, another thing is SL. Similarly, SL2 acts on the hyperbolic plane H2. And you can define the same thing, a small disk of radius theta. And the formula there is is hyperbolic sine square of theta by 2. So you can make another conjecture in SL2. I won't write it down precisely. Mu A square is bigger than something like that. So if you understand the doubling correctly, you will recover the Conti-Stan phenomenon, the endpoint estimate in the strongest form. So not only you understand the inequality, you also understand what are the extremal structures, which will be useful, I think, for as a parametric type inequality in those groups. I also want to mention one more thing, because here you can see this inequality is no longer linear. So it actually changes when you add another scalar on the higher measure. So I don't know how to make the most beautiful conjecture, but this inequality, actually these four, relies on the choice of higher measures. I just assuming the discuss measure one and just plug in everything you have. The real behavior should be some constant times quadratic behavior. Okay.
Is there an asymmetric version of this conjecture? Like
Yes, yes. So here, let's go back to SO3. If you have A and B, I'll just assume A is a set of radius θ1, and B is another set of radius θ2, and A times B will be a set of radius θ1 plus θ2. And then plug into the formula, you have a conjecture. That should be the conjecture. Okay, so here's the motivation and the construction. So any questions, Megan?
Does your theorem give any like quantitative bounds on the dependence of?
Yes, so my proof didn't really give any quantitative bound. But I will mention later a recent result by Simon Machado. He obtained some quantitative bound for a very small set. I firstly mentioned some no result and also ingredients used in the proof. I have like 20 more minutes, so probably I'll just focus on proof idea. But before that, the main early result. So what should I say here? Okay, the first one is I forgot to mention at the beginning, which I should. This is something like 4 or something, but the trivial bound is 2, because here you don't really have positive measure subgroups. So it's like generalization of Cauchy-Davenport, which is known as complement or Kneser in different settings, gives you the measure of A times B should be at least a measure of A plus measure of B if they're smaller than 1. When A equals B, you have some W2. And another thing I mentioned just now is we have solved the non-compact settings. And I promised earlier I will only talk about SL2 in non-compact groups. So I just write down this Minkowski for SL2 earlier. There's ingredients. Let us say theorem. AB are subset of SL2. So what you have is so in particular, when A equals B, so here you have A squared is at least 4A from this inequality. So that this is simpler than this 4 minus epsilon. Or you probably want to ask why this is a strict inequality and that is 4 minus epsilon. It's actually coming from construction. One has minus, the other is plus. It coming from in the symmetric space, the sectional curvature has different sign. And the sectional curvature control the volume of infinitesimal balls there in the Riemannian space. So here they have strict inequality. And maybe the most natural question I want to ask is, can we just directly apply the idea here to prove the compact case? And the answer is, of course, no. So we cannot apply any idea here. So why? One of the major idea we used, we also used later in our proof, but major idea we use here is SL2 has a natural decomposition into so have this. It's called Iwasawa decomposition. And what we do here is sort of more or less like induction, but not quite. So A and here together is a fine transformation of R. This is yeah. Let me just draw little pictures. The idea we do is you do the group decomposition. So here is the fine transformation of R side. And this is K side, the torus side. And do the same thing for B. Inside A and inside B. I'll just tell you roughly the idea or the heuristic. So here, if you choose a fiber uniformly at random, no, sorry, not uniformly, you have to design a probabilistic measure here, because if say A has lots of short fibers, you don't really want to pick short fiber. So you pick two measures here, randomly enough, and just look at the product of these two fibers. Heuristically, they are different coset and have higher dimension, and which is a nice approximation of it. But the idea is you want to reduce the problem into a lower dimensional problem, which is probably already known, so a function summation of R. Although that part is also another difficulty. So this is one of the main ideas. You just pass to subgroups. Maybe I mentioned one more. So a Fourier transformation of R is not unimodular. So for a long time, people believed a Minkowski phenomenon is not a thing in those groups, because you may have A times B have smaller measure than A if you use left measure, because you can choose B to be the collection of elements which make A really small, right? Because translate on the left and right doesn't really preserve the measures. And one of the ingredients we have in the earlier paper is a correct formulation of Minkowski inequality. So if you, I would like to write it down, although it's not really useful in today's talk. It's beautiful, I think, sort of. So you have to understand it in both left and right. You can see when mu is the right measure, you translate on the right, it doesn't contribute, preserves the measure. Mu is a left measure. So here you can see because A is on the left side, so we want to use right measure here. And B is on the left side, we will use left measure here. And if nu equals mu, it will go back to the original Minkowski. So this is one of the ingredients used. But essentially, the main thing is we want to use the decomposition, decompose into smaller dimension group, and use a random fiber trick.
So this is an Rn? Or an R?
This.
That's an Rn?
This is in a group of dimension D, and N is actually D minus the maximal complex of D. So maybe I should draw a picture. So here, why you have 2 instead of 3, right? I mentioned SL2 has dimension 3, but here the exponent is 2. So you can view SL2 as an inner part of a torus topologically, and it has a circle group as a subgroup. And then my example is a small neighborhood of this subgroup. And then you will only see the expansion on the symmetric space, which has dimension 2. So that's why I expect 2. So in general, expect N minus D minus M. D is a topological dimension. M is a dimension of the maximal proper complex sum. That's a good question. I just want to mention the formulation, and in a Fourier transformation of R, the group has dimension 2, and N there is also 2, because it doesn't really have compact subgroup. Okay, this is the first ingredient for Minkowski, non-compact version. Although we cannot really use it, but in the proof, we will transfer the problem into non-compact groups using limit argument. And the second ingredient is actually the main engine of the proof. It's an expansion gap type result discovered earlier by myself and Min. So it says any semi-simple Lie groups. Very smaller. C is absolute constant, it's 10 to the minus 1,000 or something. Then what you have is mu is bigger than 10 to the minus 12 really. So by just looking at it, it's just probably just a fine inequality. It improves true about 2 by some small constant 10 to the negative 12. But one thing I want to mention is the thing you should understand it and be helpful for the generalization of our result. To understand this input is actually a really fine structure theorem of sets with very small doubling. Because a direct corollary of this, actually proven in our paper, is the solution of inverse complement problem. Right? It's before. Maybe I should mention that. So if G is any connected compact groups, G is any connected. I just write down the simple form. Oh, yeah. And A is a subset of G. And if you know you are close to true bound, . then you can find a continuous surjective homomorphism mapping a group to a torus so that A is close to a Bohr set, one-dimensional Bohr set. The measure difference between A and K inverse of I. It's smaller than that. I didn't really mention dependence between upside and delta. I just want to give you a sort of flavor. So as a direct query, this will tell you once you have something small, actually, first is quadrat of the second. So once you have something close to 2, you can cook up a group, which is this part is actually the main engine of the proof, why the proof works. So the main idea is you need to cook up a group from small doubling. So small doubling give you a very strong constraint. So you can, yeah. I wasn't planning to mention anything about the proof there because it's very technical. I think Freddie mentioned something about approximate homomorphism. So I want to mention a few words about how we cook up the proof, just maybe 2 or 3 minutes. Okay. So maybe I just write it here. The thing is, if you already know you have a map down to torus, let's say this is a group G, and you maybe write it here, project down to torus, and then you will have a nice metric here in the torus, right? You can define distance in the torus. For example, like x and y have distance like 1/3 in the torus. And what you can define in G is you pull back this distance, and then you can find a pseudometric. So pseudometric is almost a metric, but you don't really have distance x equals 0 implies x equals y. So here, if you have a map down to torus, you will find a nice pseudometric in G, which have a nice property. That means because looking at the torus, it behaves like a straight line. Means you have any 3 points, 1 point must be in the middle of the other 2. And in the actual proof, we try to manage to find a pseudometric satisfy similar property. Means for every x, y, z in the group G, you can find a pseudometric so that the distance of x and y is within distance of xz plus minus distance of yz plus some epsilon, maybe interval of epsilon, let's just say. So you have this almost linear property. So how to obtain this? We use combinatorial argument from small doubling set, find structure property of set. For example, small doubling set cannot be a basic coverage set or KKS set. Cannot contain too many directions if you view one-dimensional torus as a generalization of directions. But anyway, using combinatorial and probabilistic argument, you can obtain some nice pseudometric, which can be seen as an approximate version of Lie algebra of the torus. And from there, you just integrate this small Lie algebra and cook up this group map down to torus. I just mentioned this because it's kind of like approximate version of pseudometric, and then linear pseudometric. And once you have that, you can find a projection, a quotient down to torus. Okay. So I probably have like 10 minutes. So I mentioned main idea of the actual proof. This format is epsilon actual proof. So, but before that, any questions? Yes.
Are you getting a new proof also for G is a billion, or are you using that as a black box?
We have a new proof of a billion. The original proof is often mathematical. I think he mentioned in his talk, the inverse theorem of insert type inequality. Here, because we cannot use analysis, so the proof is sort of geometry. By geometry, I mean you have to consider global structures of the set, not only locally. And the same proof also works for non-abelian group, which is shorter than Terry's original proof and obtain better bound actually. Yes.
You're doing, you would just applying this like to A inverse so that your K factors nicely fibers. Is that the?
Yeah, sort of. Yeah. For AB, you need to translate carefully to cancel the factor. But the different problem for SL2 tilde is this decomposition only see expansion in the other side. It cannot see any expansion in the K side. In SL2 tilde, K is R. You have extra expansion. So there, I believe our proof stop working. You have to use more geometric argument to consider the global structure. For example, here in SL2 tilde, the universal covering of SL2, which is the remaining case, open case of the Berminkowski. And difficulty there is the minimum mean matter example is multiple, not one.
You got
3 in this case?
Yeah, we expect exponential 3, but it's still open. The same proof only give you 2. Oh, I really like the proof. It's kind of easy. To understand to state. I will keep this result maybe. The original doubling type result. To make sure you remember we are going to prove this. Okay. Proof. The proof goes by contradiction. Assuming you have a sequence of counterexamples. Okay. Because the conjecture is for a sufficiently small set. Counterexample means you have a sequence of A goes to 0, its measure goes to 0, and all of them doesn't satisfy this inequality. Like 1, AN mu is a measure, G is SO3. So that the measure of AN go to 0, and it doesn't really have this inequality. I'll just write down 3.99, maybe 3.9. All these infinite set are counterexamples. And secondly, you just renormalize measure. It's just actually one step. I mean, just make it easier. So I define the measure mu n and still G. So here, mu n is actually the higher measure mu divided by mu of AN. And then as a result, I know all my set has measure 1. Now mu n of AN is 1. Because this is linear inequality, it doesn't change anything. Still doesn't satisfy this equality. And the thing changed is now mu n of G go to infinity. And the idea here is you pass to a limit. So there are lots of like suitable limit. Probably you can use like Gromov-Hausdorff limit or something. Completion of the topology once you have sort of Lie model theorem. So here we use ultra product. I will not mention too much about the ultra product, but essentially you pass to limit. So now you pass to limit, you have A infinity, mu infinity, and G infinity. Maybe I should probably mention the thing here doesn't really go like that. So you have to modify lots of things, but this is a broad picture, a rough picture. So here you already passed to an infinite setting. So you know mu infinity, A infinity, it's still 1. And you still have this inequality. Square is smaller than 3.9. A infinity. And now you have actual infinity. So now the group G looks like non-compact groups. So that you probably can apply this result. But unfortunately, there's no good topology. It's not a locally compact group. And what we can use is we use a Lie model theorem, but we have to modify Lie model theorem. We have to open a black box. But just pretend we can use a Hrushevsky Lie model theorem. It can tell you can find a map, mapping from the group G infinity to L. L is the Lie group. So let me use a different color to draw it. Maybe the proof is like you have SO3. You first pass to G infinity using ultra product, and here a Lie model. You go back to a Lie group F. And assuming you can control all the measures and make sure you remember the 3.9, this number, and L is still non-compact. So ideally, as non-compact, doubling of A is still like 3.9 infinity. Okay. So the final step is you apply Bernoulli-Kolsky.
Bernoulli works for all Lie groups.
Yes. Well, not SO2 tilde, but in this small dimensional range, it works for all Lie groups. So here 3.99 is like smaller than 4. So you know underlying group have non-compact dimension smaller than 2.
So when you take an ultra product, your dimension is still 2.
No,
Still like-
here you lose all the information in G infinity. It's like SO3 R, a group of SO3 R star, where R star is ultra product R sort of subgroup of there. There are some technical issues. I don't know. Probably I can mention some of them at the end.
This is something with respect to the harmony on the L.
Yes. So here you have a nice Haar mirror because it's a Lie group. And also the connection between the original group and Haar mirror, you have to make it super quantitative, and this is also new in the paper. It's not in the earlier ones. Okay, then apply non-abelian Minkowski. Means because 3.9 is something strictly smaller than 4, means the group really looks like R after caution out some normal compact subgroup. So you can find, I already use chi. It does use pi. So L to R. And the kernel is compact. Finish the picture. Rings. And the final thing we do is we just choose an interval in R. Choose B to be interval 0, 1, subject of R. Then B plus B has doubling 2, right? Because it becomes 0, 2. And then you just go all the way back. You lift your set B to G infinity, you obtain a B infinity have doubling 2. And then you go back to the limit argument, go back here. That means the doubling is sufficiently close to 2. Means for every epsilon, you can find subset B such that the doubling of B in SO3 is smaller than 2 plus epsilon. And this will give us a contradiction with a gap result. Okay. So I'll say one more things about to make everything quantitative. So okay, to make the proof work, I mean, so here, for people familiar with Lie model theorem, you have to use approximate groups. But once you pass small doubling set to approximate group, you already forget the constant, doubling constant. 3.9 becomes 3.9 to the power 60. And in the Lie model theorem, in Woody's original version, if you have doubling k upstairs, you will have doubling k to the 6 upstairs. You lose something here. And that is only to locally compact groups. And to Lie groups, you have to further apply Gleason-Yamabe theorem. You have to pass to open subgroups, but your approximate group may not live there. And moreover, in this go down step, G infinity to Lie groups, to locally compact groups, the kernel is G00, which are the group of infinitesimal element. It is not even a topological group. You don't really have topology there. So there are some difficulties. And the main idea is we define sort of a density function, so we go down. So we smooth our function, we convolve our original indicator function with a tube of radius epsilon in the limit procedure. And then once we smooth it, we just let epsilon go to 0. We compare A and A square, tube of epsilon and tube of 2 epsilon, study what happened inside tubes, and apply some Lebesgue differentiation theorem of Lie groups to overcome some difficulties. I think, for example, okay, maybe I should mention the final thing. By the case of our finite model theorem, we can obtain a sharp bound here. Instead of C log K, we can make it log K. Here we can make it log K, although it's not a really important bound. I think the important bound is in that. Here now this is log K after a fine version of Lie model we developed. Okay, so I'll just stop here.